Good morning, friends, and welcome lecture on forces on submerged bodies. So up till now, we have completed the video lectures on the performance of Pelton turbine, performance of reaction turbine, and before that, some model analysis and here uh, details of hydraulic turbines. Today, in this presentation, we are going to focus on the forces acting on submerged bodies. So the forces, that is mainly the drag force, the lift force, then whatever the drag and lift forces are acting on stationary bodies and formally related to drag and lift on moving bodies and the numerical based on this formulae. So that will be the content of today's lecture. So every when fluid is flowing over a stationary body, a force is exerted by the fluid on the body. Similarly, when body is moving in a stationary fluid, again force is going to be exerted by the fluid on the body. At the same time, if both are flowing, both are moving, body as well as what fluid, then also the force is exerted by the fluid on the body. And these forces exerted, that we will see afterward what we are calling them is, but always when fluid comes in contact with any kind of surface or any kind of object, okay, then always the force is exerted by the fluid on the body. And examples are there: stationary fluid, when the fluid is flowing and body is stationary, then we can say that examples are there: flow of air over buildings, flow of water over bridges. Then whatever the submarines are there, submarine ship are the example there, where the flow is also going to be, fluid is also moving, at the same time here the object is also moving. For example, submarines, ships, aeroplanes, automobiles moving through water or air. So these are the, in that case, always forces are going to be exerted by the fluid. Now these forces, what we call it as this force. So if the total force acting on the fluid is Fr, okay, now let us consider one object, a stationary object is there, and this stationary object is immersed in a fluid. Okay, and this fluid is moving with some velocity capital U. Then on this stationary object, as per the previous discussion, the force is exerted on this particular object. It is called as resultant force, Fr. And this Fr is having two components. One is the component which is in the direction of force is Fd, and the component which is in direction perpendicular to direction of motion is called as Fl. Now this Fd and Fl, this Fd is called as drag force and this Fl is called as lift force, and this Fr is going to be always resultant of this drag force and lift force. Then what is meant by drag force? Already in that diagram I have seen that the component of the total force Fr, which is in the direction of the direction of motion, is called as the drag force, Fd, and it is denoted by letter Fd. And the component of the total force Fr in direction perpendicular to the direction of motion is called as lift force, or it is denoted by Fl. And this fold lift exerted by the fluid is always in direction perpendicular to direction of motion. So lift force occurs only when the axis of body is inclined to the direction of fluid flow. If the axis of the body is parallel to direction of flow, then here lift force exerted on that body will be always zero. So to have the lift force acting on that particular object, what is requirement is there, that here that axis of that body should be inclined with the direction of flow. Then and then only lift component will exert. Otherwise, if the parallel direction is there, lift force will be zero. Okay. So now, what are, if I will take an example, a kite. A kite is kite is flowing in the air. So whatever the kite is will go the horizontal distance, maximum horizontal distance it will attain, that is due to drag force. And what are the maximum height that kite will attain, it is called as lift force. So the maximum horizontal distance attained by the kite is nothing but drag, and that is responsible component is drag. And for lifting the kite in direct perpendicular direction, the force is going to be lift force. Now we'll see now the expression. Now this is going to be very important derivation, that is the drag force and lift force acting on the stationary body. And this question many times in the examination, this kind of question they are asking. What is that question? Derive an expression for drag and lift acting on a stationary body. Okay, now let us consider that one arbitrary shaped here, this body, orange color body, arbitrary shaped body is submerged in a fluid, and this fluid is moving with velocity u. Okay, now we are interested to find out what are the total drag force acting on this particular body and lift force acting on the body. So we know that the component of the force exerted by the fluid in the direction of motion is called as drag force, and the component of force which is in the direction perpendicular to the motion is called as lift force, and resultant force is equal to Fr. This here Fr. Okay, now we are interested to find out the value of this Fd, the value of is Fl. Now for that, what we are going to consider, a small elementary area dA we are going to consider. A small elementary area, dark orange is there, that is called a dA area is there. And this dA area, first of all we will calculate the drag and lift forces acting on this particular small elemental area. And afterwards we are considering that this surface, arbitrary shaped surface, is enclosed, or it is made up of such n number of such elemental areas. So whatever the drag force we will calculate on this elemental area, we will integrate so that we will get the total drag force on this particular area, the surface. And similarly, lift force, again we will calculate the lift force on this particular small elemental area, and then afterwards this total entire lift force we can calculate by integrating the lift force acting on that object. Now here two pressure forces are there. One is what pressure, the fluid is exerting pressure, and the one component P is the pressure intensity. So pressure intensity into area is nothing but pressure force. So this PdA, and we know that this pressure always acts normal to the surface. So PdA is going to be the pressure force acting on this particular small elemental area, and we know that the shear force, another force is there, that this fluid will making shearing action on this particular area, and that force is what? Tau naught or tau naught dA is going to be the shear force perpendicular to PdA. So this 90 degrees. So PdA and tau dA making angle 90 degree with each other. Let us consider that this PdA force makes angle theta with the direction of motion. So let us PdA angle is theta. Therefore, this angle in between PdA and tau dA angle is what? 90. Definitely this angle will become 90 minus theta. So dA is the area. Therefore, here now we have to calculate the drag force and lift force on this particular lift force on this elemental area first, and afterwards we will integrate the drag force and lift force acting on this elemental area to get the total drag force or total lift force acting on the entire surface, entire body. Okay, now I told you that here first force is there. So first force is there, pressure force is equal to PdA acting in perpendicular. Okay, then now this PdA is acting in the direction of flow. Now here again one consideration is there, the forces which are acting in the direction of motion are considered as positive, and the forces which are acting in the opposite direction of motion, that is considered as negative. Now PdA is perpendicular to the surface, tau dA is tangential to the surface, and theta angle that already I described. Then the drag force acting on that elemental area is what? Force due to pressure in the direction of fluid motion plus force due to shear force. So component of pressure force in the direction of motion and the component of shear force in the direction of motion. Therefore, if you go reverse here, then here component of pressure force, PdA is having two components. PdA cos theta is in the direction of motion, and another is what? PdA sin theta. Okay, in a perpendicular direction. Likewise, here tau dA also there, we can resolve this tau dA. Tau dA cos 90 minus theta in direction of motion, and tau dA sin 90 minus theta in perpendicular direction. So this way we are now going for this. Now PdA, as I told you that the component which are in direction of motion plus sin. Now tau PdA cos theta due to pressure, it is in direction of motion, therefore plus. Then tau dA cos 90 minus theta, it is also in direction of motion, therefore plus. Then it is equal to, but we know that this cos 90 minus theta is equal to sin theta. Therefore, this will become P dA cos theta plus tau dA sin theta. Now, this is the lift drag force acting on that elemental area, but we want to calculate a drag force acting on the entire surface, and this, therefore it is equal to what? FD, we have to integrate the drag force, pressure drag force, and here shear drag force. Therefore, FD is equal to what? Summation of P dA cos theta plus summation of tau dA sin theta. And this is individually, if you integrate, then integration, area integration is there. P cos theta dA plus tau sin theta dA is the nothing but total drag acting on the that elemental, that entire body. Now the drag which is the drag component which is enclosed the pressure, that component is called as pressure drag or form drag. So the component integration P cos theta dA is nothing but what? Is the pressure drag, or it is called as form drag. And the drag force due to the shear force, shearing is called as skin drag, or it is called as shear drag. So tau sin theta dA represent the shear skin or shear drag. Like where lift force is there, we can calculate. Here we can say that here lift force is there. Again, FL, total lift force on the elemental area will be what? Force due to pressure in direction perpendicular direction of motion, and force of shear stress also in direction of perpendicular. So vertical components. So here I told you that vertical component resolution, upward forces are positive and downward forces are negative. So both are upward now. Shear stress is coming in upward direction, its component, and pressure force component is also coming in positive. So PdA sin theta plus tau dA sin 91 theta is the forces vertical component. But we know that here sin, so PdA sin theta, PdA sin theta is coming in downward direction, therefore minus sign is there. Here if you go for the figure, if you see the figure, then if you see PdA, here it acting, so PdA sin theta is acting in vertical downward direction, therefore it is negative. So PdA sin theta minus PdA sin theta plus tau dA sin 90 minus theta, but sin 90 minus theta is equal to cos theta, therefore minus PdA sin theta plus tau dA cos theta represent the lift force acting on the elemental area, and total lift force is equal to what? Total lift is equal to here integration of tau dA sin cos theta minus PdA sin theta, and therefore this is nothing but what? In the total lift force acting on that. So, and resultant force F is equal to what? We can say it as a square root of FD square plus FL square. Now these are the drag and lift forces which are calculated on the stationary bodies. Now, but every time, maximum time we have to calculate the drag and lift force on a moving bodies. Then drag and lift force body moving with a velocity u having density rho can be calculated by the formula. These are correlations. Therefore, we should not give the proof. The correlations are obtained by the physical experiment conducted by scientists. Therefore, FD is equal to, now the drag force on the moving bodies can be calculated by formula. FD is equal to CDA rho u square divided by 2. And lift force, nothing change, only instead of coefficient of drag CD, we are to consider CL. So FL is equal to CLA rho u square divided by 2, where CD represent coefficient of drag and CL represent coefficient of lift, and A is what? Projected area, maximum projected area of that body perpendicular to the direction of flow, or we can say largest projected area of the immersed body. So that is equal to A. So FD is equal to CDA rho u square divided by 2. With the help of that formula, one can calculate the drag force, and FL is equal to lift force CLA rho u square divided by 2. So only formula change is there, that the drag coefficient CD is included in FD formula, and lift coefficient FCL is included in FL formula, and resultant force FR or F, we can say, is equal to square root of resultant due to drag force and lift force. Therefore, FR is equal to square root of FD square plus FL square. So these equations are number 14.3, 14.4, 14.5 are used to calculate the drag and lift forces, or total force exerted by the fluid on moving object. Now Depending on this particular formula, we have to solve some numerical, sample numerical on the drag and lift force. So first numerical we'll go for now. Okay, so this is first numerical is there. A flat plate 1.5 into 1.5 moves at 50 km per hour in a stationary air of density 1.15 kg per meter cube. If the coefficient of drag and lift are 0.15 and 0.75 respectively, determine the lift force, drag force, the resultant force, and the power required to keep the plate in motion. This problem is there. Now nothing in diagram is required, only given data will write in our respective notations. Now the a flat plate 1.5 meter into 1.5 meter means what? Maximum area of the projection area capital A is equal to 1.5 into 1.5, it will become 2.25 meter square. Moves at, so capital U, velocity of the fluid is given as here 50 kilometer, or that plate velocity or moving velocity of that particular fluid 50 kilometer per hour. So we will become what? 50 kilometer per hour is equal to 50 into that we have to convert 10 1000 kilo, okay, divided by 3600 60 into 60, and it will become 13.89 meter per second. So remember, take care that we have to use always SI units. Density is as in already given in SI unit. Directly rho is equal to 1.15 kg per meter cube, and drag coefficient is 0.15 and lift coefficient is 0.75. Then we know the formula. All the formula is that drag lift force they asked the first. FL is equal to CLA rho U square divided by 2. Nothing is there complicated. Here see everything is given. Area already calculated. Rho. So this lift force is coming at what? 187.20 Newton. So little only formula we have to substitute the values, and then here then drag force is there. FD is equal to CDA rho U square divided by 2. Again here also there everything is given. Only drag coefficient is 0.15. The area everything is same. Only drag coefficient is 0.15. So here in that Newton, that drag force is coming as 13.37.44 Newton, and resultant force FR is equal to square root of FD square plus FL square, and it will become what? If we take the square root, solve this, so it is become 190.85 Newton. Then power required to keep plate in motion. That formula is equal to what? FD into U. Now, which force is responsible to make the power keep the plate in motion? It is not lift force, only the drag force. So the only drag component force we have to consider to calculate this value. Power required to keep plate in motion. Therefore, P is equal to what? Force in direction of motion into velocity divided by 1000. So kilowatt directly will get the component. So FD into U, and therefore already FD we have calculated. U also we are knowing, and if you kilowatt, if you divide by 1000, it will get answer directly in kilowatt. So 0.159 kilowatt is the answer. So this way, if we know the formulae in good formulae, and we have to know the notations, definitely numericals are not that much difficult on this particular force on immersed bodies. Okay, now we'll go for the another sample numerical number 2 quickly. Okay, so experiments were conducted in a wind tunnel. Okay, on a wind tunnel with a wind speed of 50 km per hour. So U is capital U is given as, okay, U is equal to 50 km per hour. We are converted into again 13.89 like previous numerical. A flat plate of size 2 meter long and 1 meter wide. So area will become 2 meter. This rectangular plate is there. Okay, so 2 into 1 is equal to 2 meter square, and the density of air 1.15 rho is given. That coefficient of lift and drag they have given. Lift force and the drag force, resultant force, direction of resultant force, and power exerted by air on the plate. Definitely what will be there? Here it is equal to what? FD, that power, to calculate power, drag force we have to consider. Direction of resultant force is equal to, that is theta direction, we have to calculate, it is equal to vertical component is FL and FD. First of all we have to calculate lift force FL, drag force FD, and then tan theta is equal to FL vertical component dy by dx, we know slope, and FL divided by FD. So we can calculate, and then after the angle we can calculate. So one by one now we'll go for again simple numerical. Only we have to put the notations now. Area A given, U knowing, so rho CD given, CL given. Lift force formula is only simple formula. FL is equal to CL A rho U square divided by 2. Everything is knowing for us. Nothing is here unknown. So therefore full FL is equal to 166.404 Newton. Likewise, drag force is equal to what? CDA rho U square divided by 2. And therefore, if FD is equal to what? We can say all things are knowing, drag coefficient we are knowing. So 33.28 Newton is the drag force. So lift force we have calculated, drag force we have calculated. Then resultant force FR is equal to, we know that resultant force is equal to what? Square root of FD square and plus FL square. And it will become what? 33.28 square plus 166.404 square, and its total will become 169.67 Newton. So this is going to be the resultant force. Then direction of resultant force tan theta is equal to FL divided by FD, and is equal to 166.38 divided by FD already calculated 33.28, and it will become phi. And then theta is equal to what? Here tan inverse of phi, and is equal to 78.78 degree, 78.69 degree. Okay, so we can convert it in minutes also there. And power exerted, now power exerted by the to keep the plate in motion. Again here we know that only drag force is required, and power force is equal to FD into U. Okay, into this will become watt, and afterwards dividing by 1000 it will become kilowatt. So it will become what? FD into U, 33.28 into 13.89 watt, and it will become 462.26 watt or kilowatt, 0.46 kilowatt is the answer. So this way, if numericals are very easy on this particular drag and lift, so only we should know the formulae. Only simple two formulas are there we have to use. One is what? Drag force FD is equal to CD rho A U square divided by 2. Lift force FL is equal to CL, only CD you had replaced by CL rho CL rho A U square divided by 2, or CL A rho U square divided by 2. Okay, then resultant force F is equal to square root of FD square plus FL square, and then afterwards then angle, if they asked, then tan theta is equal to FL upon FD. So vertical component is lift force, and horizontal component in direction is called as drag force. So this way numericals are simple, and the drag force, generally they are asking the questions for that, derive an expression for drag and lift on stationary bodies, and definitely one numerical on the moving, the drag and to calculate the drag and lift force on moving bodies. Okay, so this way we have completed the forces on, this is the unit number related to unit number 5, forces on submerged body or immersed body, that is drag and lift force. Thank you very much, and again next time we will come with very nice chapter. Thank you very much.